All right, for our final talk of the session, I'd like to introduce Omar Al-Mufti for the to present his talk. So Omar, you can go ahead whenever you're ready and share your screen up there.
Okay, perfect. Thank you, Kayla. Okay, let's see here. All right, well, welcome everyone. Thank you for sticking around. Last talk of the day.
And Omar, just a heads up, we're just seeing your full PowerPoint window right now. We're not seeing there we go. Now we're seeing it in full screen. Thank you.
All right, thank you. Okay, so for those of you who may be yearly attendees of this conference, you may be familiar with this theme of this this collaborative study between the University of Ottawa and the Geological Survey of Canada, the Champlain Sea basin here in Ottawa, and the depositional record of these fine-grained sediments. And so today, hyperpycnal flows, hypopycnal plumes. I mean, these are some of the principal sediment transport mechanisms in glaciolacustran, glacial marine basins. So, the depositional product of these types of sediment transport mechanisms, what does the sediment look like down to the micron scale? So, okay, so Laurentide ice sheet at its maximum extent. Here's just a representative map. I mean, the Laurentide ice sheet, 2 to 3 kilometers thick of ice in certain parts of Canada that, upon melting, produced a substantial volume of sediment-laden glaciogenic meltwater discharge that was dispersed into the glacio-isostatically subsided Champlain Sea basin. And so the study area for today is the city of Ottawa. Right, so why study the Champlain Sea basin? Well, it's of great societal interest for a number of reasons. One is the potential susceptibility to landsliding, retrograde landsliding. The second is the character of these fine-grained sediments as regionally extensive aquitard in the Ottawa and St. Lawrence River valleys. Okay, so the study area, it's in a municipality in East Ottawa called Orleans. Okay, and so 2 boreholes, one called Voyageur Creek and Bilberry Creek, separated by a distance of about 3 kilometers. And they were drilled in fall 2019, and cores were extracted. And these cores were sent to Quebec City, the INRS laboratory, and each core was scanned using a medical grade X-ray CT scanner. And from that CT scan data set, in an earlier study, we were able to reconstruct the stratigraphic makeup of the succession at the base of the succession. And we identified 5 mud-dominated lithostratigraphic units. So what are these mud-dominated lithostratigraphic units? Well, at the base of the succession, call it Unit 1. And Unit 1 look like classic varves, called mud rhythmites. Okay, there's a distinctive dark layer, clay-rich winter layer, and there is a silt-rich, planar laminated summer layer. That is in turn abruptly overlain by a unit of bioturbated mud. We call it Unit 2. It's thoroughly bioturbated. Those bright grains that you see in the X-ray CT scan image, that's pyrite filling burrow fills. These bright grains that you see at the base of, in the lower part of this X-ray CT scan image, those are dropstones. Unit 2, that bioturbated unit, is abruptly overlain by this package of, this interval of diffusely stratified to structureless mud. We call it a banded mud unit, that of Unit 3. It's the thickest unit in the succession. That is in turn abruptly overlain by well-stratified mud of Unit 4A. And this well-stratified mud is intercalated with diffusely stratified or structureless mud intervals. And you can see that in the X-ray CT scan image. Here we have well-stratified planar lamination with load casts, and this would be a diffusely stratified or structureless mud interval. That in turn is overlain by deformed mud. So, in this previous work, each bed is exhibited by this very characteristic signature in its what we call HU, Hounsfield units, a quantitative measure of radio density. And so HU values, they vary primarily with properties that influence bulk density, namely grain size and porosity. So each bed in the succession, and here we're looking at Unit 1, those mud rhythmites. Each bed exhibits an increase in HU that corresponds to an increase in silt content That is then followed by a decrease in HU that corresponds to a decrease in silt content. And so that increase in silt, that's interpreted to be the waxing phase of glaciogenic meltwater discharge in the basin. The peak HU, that maximum HU value, that corresponds, what's interpreted to correspond to peak meltwater discharge conditions in the basin. So that peak HU, that corresponds to the siltiest part interval of the bed. That is in turn relayed by a waning interval. This is the waning phase of glaciogenic meltwater discharge into the basin. And so these bed scale HU profiles can be considered as flow hydrographs. They reflect variations in glacial meltwater discharge. And this is just a simple representation of a single bed showing the change in flow discharge, the seasonal change in flow discharge. And it's important that every single bed in the entire succession is characterized by this rhythmic profile in HU, upward increase in silt followed by upward decrease in silt. And so we interpret each bed to be glacial rhythmite, to be a varve. That's right, an annual deposit, deposited within 1 year. It actually lines in quite nicely with the radiocarbon dating that's been done by other workers collaborating on this project. So, okay, what this shows, again, here's this, the stratigraphic makeup of the succession, units 1 through 4A. This illustrates the variation in bed thicknesses throughout the succession. And so beds in Unit 1, again, Unit 1, these are mud rhythmites interpreted to have been deposited in a glaciolacustran setting. Beds are about 2 centimeters thick. And across the Unit 1 to Unit 2 transition, they abruptly thicken to 4 centimeters, one borehole, to 6 centimeters average bed thickness in the other borehole. And so this change from Unit 1 to Unit 2, this is the change from the glaciolacustran phase of the basin to glacial marine phase. That's the incursion of the Champlain Sea. So the mud goes from nicely stratified, classic textbook varves to biortubated mud. That biortubated mud, in turn, is abruptly overlain by this interval of banded mud. The lower part of Unit 3, average bed thickness is about 10 centimeters. The upper part of Unit 3, average bed thickness is about 14 centimeters. And in the upper part of the succession, Unit 4A, average bed thickness is 20 centimeters. So this is, I've looked at a large suite of thin sections collected throughout the succession. And what we saw was that Unit 1, there's no burrows, there's no biortubation. Unit 2, there's abundant burrows. Okay, it's biortubated mud. Unit 3, there's a few burrows in the lower part of the succession where average bed thickness is about 10 centimeters. But where average bed thickness increases to 14 centimeters, you lose the burrows. There are no burrows, no biortubation. And likewise, in the upper part of the succession, there's no biortubation. And so it seems that there's this threshold rate of sedimentation, about 14 centimeters per year sedimentation, that these myobenthic critters can no longer survive. And so sedimentation rate had a major control on biogenic activity in the seafloor sediment. Also, I'll add is that pyrite, framboidal pyrite, where we have burrows, we have framboidal pyrite. There's no framboidal pyrite when you have an absence of burrows. And so there's a direct correlation between biologic activity and diagenetic products in the succession. And so, again, the basal part of the succession, mud rhythmites, that's the glaciolacustran phase, biortubated mud, banded mud, and well-stratified mud correspond to the glacial marine phase of sedimentation. And so the interpretation was that due to the freshwater basin fluid during the glaciolacustran phase, inflowing sediment-laden glacial meltwater discharge could easily plunge to the lake floor as a negatively buoyant hyperpycnal flow. And similarly so, Unit 4A time, the upper part of the water column being freshened would have enabled inflowing meltwater discharge to plunge as a hyperpycnal flow. The interpretation for Unit 3 time, where we have mostly a saltwater basin fluid, well, due to the density contrast between the inflowing glacial meltwater discharge and that of the basin fluid, inflowing flows would have continued in the basin as positively buoyant hypopycnal plumes. And so the question began, well, okay, the resolution used with this X-ray CT scan data set is about half a centimeter, 0.5 millimeter scale. But what about microtextural characteristics at the sub 0.1 millimeter scale, the micron scale. What are the microtextural characteristics of the deposits of these types of sediment transport mechanisms? And so prepared samples made thin sections, which dealing with unconsolidated, unlithified mud, it's a time-consuming process, but nonetheless, we made thin sections and polished thin sections, I would add. Examined them under the optical microscope. We coated the polished thin sections, then examined them using scanning electron microscopy. Okay, so what do we see? Well, there are two distinct mud microfacies. They ask, okay, well, what's a microfacies? Well, we all know a facies is a distinctive body of rock with unique characteristics that differentiates it from blah, blah, blah. Well, a microfacies simply is a distinctive body of rock or sediment identified at the thin section scale. And there are two microfacies that were identified. Microfacies A is structureless mud. And there are a number of variants of structureless mud. Structureless mud could be inversely graded, as you see here in these micrographs. They exhibit an upward increase in silt content and upward increase in silt grain size. Structureless mud could be normally graded. You see an upward decrease in silt grain size, similarly an upward decrease in silt content, or structureless mud could be massive. This electron micrograph, the lower electron micrograph, K feldspar and albite, these are medium to coarse silt-sized drop stones within a winter layer, all within Unit 1. Okay, that's microfacies A. What was the second microfacies that we identified? Well, planar laminated mud, of which there's two variants. Mud could be laterally continuous, where you get texturally differentiated silt-rich and clay-rich layers. So here we have two photomicrographs. The upper images are photomicrographs. Silt-rich layers, clay-rich layer. Silt-rich, clay-rich. And likewise in the image on the right. The lower examples, these are electron micrographs. The textural sorting is incredible. The silt-rich layers are moderately to well sorted. They consist almost entirely of silt-sized sediment. The clay-rich layers are comparatively more poorly sorted. There's also another variant of planar laminated mud. You get laterally discontinuous silt layers, but even with these laterally discontinuous silt layers, photomicrograph here, you can see this layer of silt. It's laterally discontinuous, as the name suggests. But internally, the silt layer consists of moderately to well-sorted silt. And so all of the sediment in the succession either consists of a stacking arrangement of these two, microfacies A and microfacies B, okay, or different, rhythmic alternations between the two. So let's begin with Unit 1. Okay, well, what do we see? Well, the winter layer, it's structureless mud. Looks like that in A and B. This image captures the contact between the winter layer and the onset of the waxing phase, that onset of glaciogenic meltwater discharge into the basin. You can see in this electron micrograph the upward increase in silt content. Start to see the onset of lamination starting to develop. E and F shows the character of planar lamination. And that's microfacies B, planar laminated mud. Note the scale bar in F. That's a 10 micron scale bar. This is silt-rich and clay-rich lamina developed at a few tens micrometer scale. I mean, and the textural sorting is incredible. So just to comprehend the physical sediment transport sorting mechanisms taking place right down, right next to the bed. Biortubated mud, as the name suggests, it's biortubated. It's thoroughly biortubated. There are a number of burrow fills that were identified, clay-rich burrows, such as shown here. Another variant, silt-filled burrows with a clay-rich lining. Some burrows were filled with rhomboidal pyrite. We wrote a paper on these myobenthic, myobenthic biortubation, the controls on burrows and diagenesis, which should be coming out hopefully in the next few months. It's gone through review. Unit 3, banded mud. It's one of the thickest units in the succession. And so you look at the X-ray CT scan image there on the left, okay? And at this macroscopic scale, it consists of texturally diffuse stratification, okay? Dark colored layers and light colored layers. So what exactly are the dark colored layers composed of, and what are the light colored layers composed of? Well, the dark colored layers, it's massive mud. It's massive structureless mud, such as shown in electron micrograph A here. The light colored layers, so this was surprising. The light colored layers consists of laterally discontinuous layers of silt, and the silt layers are moderately to well sorted. And the entire succession of this nearly, in the westerly borehole, nearly 30-meter thick unit of mud, it's either microfacies A or it's microfacies B, and this rhythmic alternation between the two. So where you see dark color layers, that's A. Where you see light colored layers, that's B. Okay. Near the top of the succession, Unit 4A, that's where we have these well-stratified intervals, as you can see in the upper part of this X-ray CT scan image, and these more diffusely stratified or structuralist mud intervals. Well, what does the well-stratified mud look like? It has the same textural organization, the same texture as that of Unit 1 mud. It's planar laminated, silt-rich, and clay-rich interlayers. Okay, again, note the textural differentiation between the two layers. The thing that was identified in Unit 4A is the appearance and abundance of mud interclass. So this is an example of a mud interclass. Okay, it's just, its origin, it's derived from seafloor erosion of somewhat semi-consolidated, cohesive mud. Okay, there's no fabric to the interclass. Okay, so this is interesting. So the red dot is this excavation site. This was a construction site, about 3 to 4 kilometers to the northeast of Borehole BC 16 that we visited a few years ago. It's now the story of a 20-story luxury condo building. But at this outcrop, what we see is the same sedimentological features that we see in the borehole. So just to go back, what you see in the CT scan image is planar laminated. There's an abundance of load casts. All of these kind of features that you see here, they look like lenses. They're actually load casts. They're a consequence of soft sediment loading. And we see the same textural features in outcrop. Again, remember that waxing to waning rhythmic profile that every bed is characterized by. We see this in outcrop as well. So it's not exclusive to the boreholes. Okay, so here's an example of a bed. Upward increase in silt content, you start to see the greater abundance of silt layers appearing in the sediment. This interval of planar laminated load cast rich mud, these are load casts. Okay, look at textbook flame structures along their bases filled with silt, laminated silt clay rich layers. That is in turn overlain by what can be interpreted as a waning phase of discharge. So again, here's the waxing phase. This is potentially corresponding to peak meltwater discharge and the waning phase. So again, we would interpret this entire bed to be a VARV, okay, an annual deposit. And just to show, the same character that we see in the boreholes, planar laminate, well-developed planar lamination and an abundance of mud interclass. Okay, so to summarize, well, the entire succession of this glaciolacustron, so at the base is a glaciolacustron phase, overlain by a sediment deposit in a glacial marine setting. And all of the mud consists of either of two microphases. It's either structuralist mud, and there's 3 different variants, or it's planar interlaminated. It could be laterally continuous planar lamination, it could be laterally discontinuous. And so the deposits of fine-grained hyperpycnal flows, well, they consist mostly of laterally continuous, several micrometer thick silt clay-rich layers. The deposits of hypopycnal plumes, well, they're composed of structuralist mud dispersed with laterally discontinuous silt-rich layers. And so, this excellent grade size segregation of these planar laminated silt-rich and clay-rich layers, right? Well, this necessitates efficient sorting mechanisms taking place in the very near bed region, particularly of the sediment gravity flow. And so, this occurrence of these two end-member types should be, further explored in future studies of other fine-grained glaciogenic successions. And thank you all very much for your time.
Thank you, Omar. Thanks for presenting your work and